It's a real pleasure to be here and share with the broader community what we're up to at Quantum Benchmark, give you a sense of what the problem is we're solving, how we're solving it, and why it matters to you. So what we're trying to do is develop a fast lane. What we, in fact, are doing is developing a fast lane to quantum advantage with our TrueQ technology. So let me tell you a little bit about that. But first, let me explain the problem. So there's a new paradigm with quantum computing. We're building a new mode of computing from scratch, and it's very different than conventional computing. So conventional computing is similar to a high-speed train. A high-performance computer is something which is discrete and predictable. We know if you're trying to go from A to B, we know you can get there. The only question is how fast is it going to go? Can you get there or not? With a quantum computer, we have the problem of dealing with errors. You've heard about that throughout the day. That's because quantum computers are fundamentally continuous and error-prone, analog and error-prone. So it's analogous to a rocket ship. With a rocket ship, we can get to totally new places, but we have to deal with new challenges. We have to deal with the fact that the rocket ship can go off course because of turbulence, because of thruster fluctuations. And so we need to continuously monitor and control the errors in that three-dimensional space. Now, in a quantum computer, we're dealing with that problem in a much higher dimensional space. So what got me into this? So when I was at MIT many years ago, we were involved in the first 3-qubit quantum computing experiment. And what we discovered was we wanted to systematically characterize all of the error pathways in that process. And we realized that that number was greater than 2 to the 12. That's thousands of different error modes on a 3-qubit quantum computer. I realized that the way we did it, the only way that was known at the time, wasn't even reliable. Not to mention that measuring a few thousand error modes is the maximum pain you'd want to inflict on an MIT grad student. So we realized better solutions were needed as we aimed to scale up to dozens, hundreds, thousands of qubits. And so that became one of my career arcs academically, focusing on solutions for overcoming this problem, characterizing and overcoming errors. And so what that did is prompted us to form a startup. With these great advances we've seen, these breakthroughs we've seen in the past half dozen years in quantum computing and multiple platforms, we decided that we should take our cutting-edge academic research and produce a tool set that was useful to the quantum computing community to accelerate us towards quantum advantage. And so the first product we developed was called TrueQ Design. This is something we launched about 2 years ago. Google has graciously allowed us to announce that they were one of our pioneering customers. They've been using our software for about 1.5 years. So how does it work? Well, TrueQ software is something that runs on your lab control quantum computer, and it interfaces with all quantum computing platforms. And what it allows you to do is diagnose the full system errors with scalable tools that are robust. It allows the hardware teams to optimize the hardware and the pulse design, and it enables fast calibration and tune-up routines to overcome these performance fluctuations. We have this great testimony. We work with superconducting qubits. We work with ion traps. The ion trap team at Alpine Quantum Technologies gave this great quote: "Before TrueQ Design, we simply lacked the tools for verifying that we are on the right track towards scalable quantum computing." Now, some other data I can show you is data we took on an IBM device, one of their public devices. This is, in fact, the Yorktown device. Now, keep in mind, this is one of IBM's first devices they put on the cloud. So this does not reflect their state-of-the-art capability, but this reflects our tools for diagnosing these errors. So what we're looking at here is a heat map for the errors on a 5-qubit chip. We're looking at a small subset of the errors. And just to fit on the slide, basically. And what's interesting about this figure is we're just doing a C0 gate on qubits 0 and 1 and idling the other qubits. And so what you see in the figure is that first column is the errors associated with the C0 gate on those 2 qubits. And the fact that the colors are dark means the errors are relatively low. But what you see is elsewhere on the chip, we have the qubits are lighting up. And that's because there are off-gate errors induced by the control field on the 2 qubits that it's trying to target, which limit overall performance of the device. So clearly what this is showing is that more sophisticated error diagnostics are needed both for the hardware teams to understand how to improve their hardware, and as I'll get to later in the talk, for users to improve the performance you can achieve with the hardware that's handed to you through the cloud. Another example from our work with Google is looking at their Sycamore chip, and the takeaway message from this diagnostic is that if we do a CNOT on qubit 0, 1 in isolation, then unfortunately there's been some font issues there, so I apologize for the messiness. If we do a CNOT in isolation on qubits 0 and 1, we see a particular fact pattern in the errors. What's interesting is the two tall errors in blue are IZ and ZI errors. Those are easy to correct via phase referencing. So that's an illustration of how this diagnostic information is useful for increasing the performance of the device. But then when we also add in a CNOT on qubits 6 and 7 in parallel, the error model barely changes. So this reflects the increased capability of the tunable coupler technology and design that Google developed. Now, a simple analogy for this is basically we are navigating through icebergs when we're doing quantum computing. So on the one hand, we have a few figures of merit we can talk about as error rates associated with gates, and that's just the tip of the iceberg. Ultimately, there's a massive threat under the water, which is limiting the performance of our quantum computer. And understanding the scope of that full iceberg is relevant to the hardware teams, but what's important for this audience is understanding that it's also relevant to you. You're trying to compute with the noisy hardware that is being put on the cloud. Today we've heard all about error rates, we've heard about gate error rates, we've heard about the challenge of crosstalk from all the big hardware vendors. And here we're today announcing tools for the user to overcome the residual errors that the hardware teams have not been able to remove and get better performance out of your quantum computations. And so that platform we call TrueQ Accelerate, which we are now launching. It is applicable across all user applications, drug discovery, material science, quantum chemistry, machine learning, whatever it is you're exploring with quantum computing. It works across all hardware platforms. In fact, there's a universal interface and transpiler that's user-friendly that allows you to run your code on whichever hardware you want, but more importantly, it's error-aware. So it has tools to identify and overcome the errors to determine the optimal means of implementing the algorithm on the hardware. It allows you to optimize the way you implement the application on that hardware, called co-design, and it also allows you to get an understanding of the solution accuracy when running computations on noisy hardware, which is very important. Why is it very important? Because now with Google's announcement, we're on the cusp of an era of quantum computing outperforming conventional HPC computing. Why do we want to do quantum computing? Because it can solve problems that those systems can't solve. But now you're doing this on a noisy processor. How much can you trust the solution you get? You need tools to verify the accuracy of the solutions, and that's what we can provide. So here's an example of our tool running on IBM Quantum Experience. This is on the Melbourne chip, which had 14 qubits at the time that we ran this. What this plots is the x-axis. The bottom axis is the circuit depth. As you increase the length of the computation, solving a harder problem, we look at, on the y-axis, how the solution inaccuracy grows because of the errors impacting that computation. And what you see in orange is the native performance of IBM Quantum Experience with its native Qiskit compiler. And then what you see in the blue is the performance when that circuit is run through our transpiler. And what you see is a massive reduction in the error rate with improved accuracy and an overall stable performance of the solution, which is part of how we can predict the accuracy as we trend into this regime of beyond quantum supremacy. So I've already mentioned what it does. It reduces errors, it stabilizes performance. John Martinez, who we heard from this morning, was very gracious in sharing a quote for our press release where he said basically he couldn't imagine building a computer without our tools. So that was a pretty strong endorsement from someone who knows what they're talking about. And the key message here is that this is available now to all quantum computing users. So we're very excited to get this software and this technology in the hands of the people trying to discover quantum advantage through quantum computing. You can contact us if you're interested in the software. It's also available on the application showcase of the IBM Quantum Experience. At this stage, I'll take a minute to show you a slide which my colleagues absolutely love because it puts the full quantum computing landscape into one picture. This ties in with what Peter Chapman mentioned this morning about the importance of benchmarking tools to understand comparative performance of different hardware platforms in a way that's relevant to the applications we care about. And so the first thing we have to realize is that just counting qubits is a terrible way to assess the capabilities of hardware. It's as naive as assessing the value of some number of diamonds by counting the number of diamonds. You need to know a lot about the quality of those diamonds to know anything about their value. What the 3 C's of quality. And so in the quantum computing landscape, it's the same thing. We need to understand a lot about the errors that tell us about the capabilities of that platform. But the very lowest level thing to do is just talk about the achievable circuit depth. That's how far can you compute before you get an error. And so what I've plotted here are circuit depths ranging from the tens to the hundreds to a million. This is sequential operations across a larger and larger number of qubits on the bottom axis. Now, if you have 10 to the minus 3 error rates and you have 1 qubit, you can do about 1,000 operations in sequence before you're likely to get an incorrect solution. If you have 1,000 qubits and 10 to the minus 3 error rates, you can only do about 1 sequential operation across all those qubits before you're likely to get an incorrect solution. So the challenge with scaling up hardware at a fixed error rate is that you're sliding down this slope. Now, there are solutions to overcome this, but just be aware that that's a challenge. Now, the other thing people care about is the HPC horizon, which is how far do we have to get on this graph to be outperforming high-performance computers? And now there's lots of different ways to draw that line. There's strong simulation, there's weak simulation. So I've kind of interpolated between 2 common schemes. This is not the be-all and end-all. This is not a scientifically comprehensive assessment. But it's so hard for classical computers to simulate quantum computers that the details of this line aren't going to change much depending on what you do. So this sets essentially a boundary or a threshold for what I call the quantum discovery regime, which is quantum computing hardware that's capable of exploring problems that are beyond the scope of HPCs. So a new era of discovery with a new computational tool, a quantum computer. So then the question is, where are we now? And so what we can look at is some of the published data out there. And so in green, I'm plotting the achievable circuit depths on increasing number of qubits with the Alpine Quantum Technologies ion trap quantum computer. This was a joint project between Quantum Benchmark and Alpine Quantum Technologies using our cycle benchmarking tool. Peter Chapman this morning mentioned the importance of benchmark metrics that are relevant to applications, and that's exactly what this is. We take an application, we take a circuit, we break it down into components, and we're able to characterize the components of that circuit as they relate to the overall performance of the circuit. And so what you see is a very excellent performance. This is using this all-to-all connectivity of the ion trap with very low error rates, which is very promising. Unfortunately, it's only on up to 10 qubits at this time. This data was actually taken 2 years ago, so AQT has made big performance gains since then, and I'll let them make those announcements when the time comes. In red, we have the recent announcement of Google, this major milestone to which we should all appreciate, and I certainly congratulate them on their demonstration of incredible control over a 53-qubit system. And what's important is that these performance dots, the depth 14 and depth 20 circuits they demonstrated in that paper, are on the boundary. They're on this horizon. And that's exciting. That means now, with the next steps in hardware, we're able to explore this regime of quantum discovery. We're able to start looking for quantum advantage in this new valley we can access. And whether we find it or not is up to us collectively to work hard and roll up our sleeves and figure out which problems we can solve with this new resource. And then I'll just end on the note that how we fit into this picture is that if you're at the lower end of this quantum discovery regime, you're looking for exploratory problems that might be solved by a quantum computer more efficiently than a conventional computer, than an HPC. But once we move way up to the top of that graph, we are exploring an area where we know we will get disruptive quantum capabilities with a quantum computer. But that involves scaling up many, many orders of magnitude of performance. One pathway to get there is through quantum error correction, and that's certainly a pathway which we're very focused on helping the hardware teams achieve through error diagnostics and error suppression. And so this is how we fit into the big picture. Our TrueQ design tools to help hardware platforms reach the lower edge of this graph with multiple qubits, and our TrueQ Accelerate toolset for co-design of applications is designed to move people up and to the right, so achieve the truly disruptive capabilities of quantum computing.